All right. Well, hello, everybody. Thank you for attending another one of the Siemens SINUMERIK webinars. I am just going to be your moderator today. My name is Chris Pollock. We are going to have two colleagues of mine that are certainly subject matter experts on the topic that we're going to delve into. So sit back, relax, and enjoy. I think you're gonna like it. First things first, we will be recording the event as always. So post-event, we will send out the traditional link for the video, and then certainly the video is going to go back onto our YouTube channel as we normally do. So there'll be multiple sources for you guys to get back to this information. All your microphones are muted, just to give some respect to our presenters. We will be doing a Q&A process at the end, as always. So what I would suggest is, as we're going through, you hear things that you want to dig into deeper, or just questions come to mind, plug them right into that Q&A panel. You'll see there should be a little questions tab there for you, and then we will go through them all in the end for sure. So today, I'd like to introduce everybody to my colleague, Brian Baumgartner. A lot of you probably already recognize Brian. Brian has done certainly a few of our webinars here. He also runs a lot of our training classes for us and works very closely with our key targeted OEMs. So Brian, welcome to the program. Say hello to everyone.
Sure thing. Yeah, thank you very much, Chris, for the introduction. Hello, everyone, and welcome. I'm very glad that you could all join us today. As Chris said, my name is Brian Baumgartner. I'm a SINUMERIK CNC systems engineer, and today's session focuses on optimizing SINUMERIK systems for speed, smoothness, stability, and synchronization. So some of you may be working with these challenges every day, while others may simply be looking to deepen your knowledge. Regardless of the level of experience that you bring with you to the webinar today, you're in the right place to expand your knowledge and gain some practical insights into both tuning and optimization.
Perfect.
So yeah.
Well, with that, Brian, I know you're ready to rear on, so I'm gonna give it over to you. We'll fire up, I guess, probably your first slide. We'll let everybody see your shining face, and then I'll jump in the end when we do the Q&A. So we'll talk soon.
Awesome. Well, thank you, Chris. So in just a couple minutes, we're going to be taking a deep dive into a new tool called the SINUMERIK Tuning Center. And this tool helps users make sensible tuning decisions, verify the results of tuning, and apply changes in a controlled and repeatable way. But before we do that, I'd like to take just a little time to introduce the team and set the stage for our keynote speaker, Alex Kubik. So this is a team that hopefully some of you already know. If you don't know us, say hello. We've got all of our email addresses there on the slide deck. We are the technology application team in the USA, and we're hosting this webinar that you're seeing today. Our brick and mortar facility is located in the greater Chicagoland area. Dan Struble, who you see over here, runs that facility and is in charge of all of our training classes that operate from that facility. Adam Caves is a technical systems engineer, just like myself. The two of us focus on a lot of service and commissioning topics, but I think I can speak for the four of us on the team that each of us are a jack of all trades. So we know a little bit about a lot of things, and there's some things we know a whole lot about that we're specialized on. Then as we move over towards the East Coast, you can see myself, Brian Baumgartner. I'm based in the state of New York, like Chris Pollock. Chris is our team lead, and many of you probably know him as Mr. CNC. Thanks again, Chris, for the introduction and getting this all together. So to introduce the DEX just a little bit more, DEX is Digital Experience Center. We offer a couple different programs to meet our key mission, which is to make SINUMERIK technology accessible to everybody who needs it. So the first program that you should know about, it's our official TAC classes. These are conducted both virtually as well as in person. I actually was just doing a class this week. It was Shop Mill Level 1 training. I hope some of you have made it from the training into this webinar. I know we talked about it. There's all kinds of classes, but definitely you can go to this site, usa.siemens.com, CNC training, to get more information on it. Another one of the programs that we do in the Digital Experience Center from the USA is called the VTAC. So that's the Virtual Technology Application Center. And this kind of focuses on two different YouTube channels. We've got a very well-established, amazing, and awesome channel called Mr. CNC. This has a whole plethora of content on it, and it could be your first stop to find all kinds of things as long as they're to do with SINUMERIK CNCs. There's a new channel that I'm also excited to talk about that's called Mr. CNC Insights. So this channel gives a home to those of us who focus primarily on service and commissioning topics. So everybody do check that out. It's a lot of fun. I've been doing a couple videos there, and we're constantly adding to those videos on the channel. We also have a direct customer engagement campaign. So all of us that you saw on that first slide are available to talk directly to customers. Normally we'd schedule something like an office hour, so it'd be like 1 hour with the trainer, and we're happy to get in touch with you guys, try to understand what challenges you have, be they either at the beginning to figure out what software or hardware could be best for an application need you have, or even somewhere further down the line. Maybe you already have the software, but it's not behaving how you thought it would. If there's a new part you want to program and you just want to gut check to see, am I doing it right? We also have the content manager because we have so much content. It's nice to be able to come to one document and see where all of our content is located. So you can get here, you can click the link. There's also a link on our main page for the TAC classes that you can get to. Next, we have a contact list. So those of you who are in the webinar today, you may have learned about it because you're a part of this list. This is how you can stay in touch with us, really, and be alerted of when the new webinars are coming out so that you can be the first to get that knowledge. You can participate as you wish in the chat as well as in the Q&A when you come live. So that's an awesome benefit you get. And finally, we have a number of social media channels. You're welcome to follow us here. And now we get to the fun part. So now we're going to start to talk about the content for the day, which has everything to do with tuning and optimization. And before we get going to set the stage for our keynote speaker, I wanted to talk just a little bit about traditional machine tool tuning. I know I've had a fair amount of experience with that in the past, and I suspect some of you on the call probably have as well. So with traditional machine tool tuning, there's kind of two constraints that are built into it, two different categories. And the first category is knowledge. So if you're going to get into this, before you get going, you have to have a certain amount of knowledge. And then there's two different paths you could seek to get the knowledge when you're tuning a system traditionally without the new tool we're talking about today. And one path would be to develop some in-house knowledge. But there's a challenge with that because if you don't already have the in-house knowledge, it's going to take you some time to acquire that knowledge. The other thing that you might do to meet this prerequisite is you might decide to hire some outside experts, and that's a great path to go down as well. But we are going to potentially have a challenge because now we have to accommodate their schedule. They're not in our house, so we've got that to contend with, and there's also a cost. So there's a supply and demand kind of force that we have to contend with. There's only so many experts, and so we have a limited supply, and they're in high demand. The other built-in constraint is the process itself with traditional machine tool tuning. So the traditional process can be really time-consuming, even for the most experienced of users. I know sometimes it could take me half a day to tune an axis, maybe a whole day just to dial it in. And part of that is because the normal process does require some trial and error. So you're going to make some assumptions, make some decisions, and then you're going to have to do a cut test. You might end up back at the drawing board afterward, and you might even forget what you did test and what you didn't test. So that's coming back to the standardization. So there's a bit of a lack of standardization. We might get kind of lost in this process, and maybe we even repeat ourselves through it. The one thing I think that also relates to the lack of standardization is the way that one person tunes, one expert, might be very different than the way another expert tunes a system. And then how do you kind of bring those two together so that throughout a facility you have a standard tuning versus maybe a little bit of a different tuning per machine, depending on the expert that tuned it. And this brings us to the next slide. So now I want to take a minute just to challenge the standard approach because clearly there are some areas that we could improve. And here's some key questions I put together that could drive innovation. So first off, how could we reduce the dependence on expert level knowledge? So there's a little bit of a gate here. How can we open that gate and let more people be able to tune systems? Next, how could we shorten the learning curve for tuning? So if you were to develop in-house knowledge, like we looked at last time, it could take a while to get that knowledge. How can we make that easy? Next, how can we make the tuning process faster and more efficient? This relates to those process-related challenges rather than the knowledge ones. Traditionally, it takes some time. Clearly, there's room for improvement there. And then the last one is, how can we standardize tuning for consistent and repeatable results? Next, we get to Alex. So here I get to introduce my colleague, Alex. Good morning, Alex, or should I say good evening over there?
Yeah, right. Hello, Brian. Yeah, rather late afternoon here.
Awesome. How are you today?
Yeah, I'm totally fine. Thanks.
Very good. So for anybody who hasn't met Alex yet, he is the project manager behind the SINUMERIK Tuning Center, and he's been closely involved in its development. Before we dive in, I'd love to get a bit of your perspective, Alex. Have you yourself worked very much with traditional machine tool tuning?
Yes, I did. Yeah, so before I started within that project, I did that job for about 15 years. So I've been really hands-on gains and filter parameters and all the dynamic parameters in SINUMERIK.
Wow. So I presume you're familiar with some of the constraints and challenges I just talked about then.
Yeah, I can remember all of them.
Yeah. So at what point did, I guess, your career evolve into what it is today, managing the SINUMERIK Tuning Center?
Yeah, it's slightly changed from tuning machines to explain to customers how to do it, and doing nice reports so that they can also understand later on what happened and why I made that decision. So, and then at each visit at the machine, it turned out to be like a training, that a couple of people behind me and asking questions, and then finally we said, okay, we need to create something that helps people to do it without attending trainings. So everybody who is familiar with commissioning and machine tools should be able to get a reasonable setting.
Awesome. Well, thank you, Alex. I think this sets the stage for what we are about to see. So you just talked about how initially you made reports, you do the traditional tuning strategy when you'd go on site, but it started to evolve into something else where you wanted to be able to help them to do more, maybe with less training. Are you ready to present to us the new product, the SINUMERIK Tuning Center?
Sure.
Awesome. So I'll hand it over to you then.
All right, thank you. Yeah, so what will we see today? Let's dive into the main facts. The application STC supports two main scenarios. So on the one hand, it's the tuning of the CNC axis, and yeah, we call it guided tuning. So you will hopefully see in the next half hour what that means. And on the other hand, I think you all know situations where it's good to have a deeper analysis of the axis signals and how the axis moves, how it stops, how much power it takes. So for that kind of general diagnosis, this tool also provides a trace application, which can record and visualize all kinds of SINUMERIK and dynamic signals. But today, we will mainly focus on the tuning part. And the good news is that SINUMERIK Tuning Center can be installed on any Windows 11 PC. And now with the latest version, you don't even have to install other Siemens SINUMERIK software. You just need the download package of SINUMERIK Tuning Center, and it has all which is required to be able to connect to the SINUMERIK controls. And these controls, they can be like SINUMERIK 1 and also 8 to 8. So there's still solution line controls supported, including 840D ESL.
Wow, that's actually pretty interesting. When I first learned about the SINUMERIK Tuning Center, I didn't realize that it was compatible across the whole platform. You say I can use it not just on SINUMERIK 1, but if I have an 828D or one of the older 840D solution lines, it works fine with those too?
Yes, it does.
Awesome.
So you just have to make sure that your software version on the 840D is not too old, but if you have 4.8 and newer, then you're fine.
Excellent.
Okay, then. So why is STC useful? We call it guided tuning because this application gives you procedure that will make sure that you can't forget important steps, and that you do all the preparation which is required to get useful recordings and useful tuning results. So you don't need to attend a training. It should be more or less self-explaining to use it, and it also helps you to create part programs and all the measurement settings, so they will prepared automatically. And okay, it works in that way that the application will read and write parameters from the control and from the drives, and downloads the part programs. It also uploads the trace recordings, so you don't have to care about that stuff. It's typically used for finishing the commissioning of a prototype machine or of a first machine of a series. And for the ones who already know auto servo tuning, which is typically called AST, so you still can use it. It's not that we will cancel it, but STC has another focus. So still, the feedback loop tuning is a very important step, and here also in STC, it's the very first step which we recommend. But if you're already familiar using AST, you can do that and import the results into your tuning project of STC.
So if you could hold on just a second, Alex, I do have a question, because one of the bullets says it's used for the finishing and commissioning, typically of a prototype machine. But are there other situations, perhaps throughout the machine's life cycle, when the tool could be useful? I'm thinking about things like if you're changing the ball screws, or maybe you get a new part that's significantly larger than one of the parts you ran in the past. Might there be some benefit to running this tool kind of midway through the machine life cycle?
Yes, so especially when the machine builder does service on the machine and changes parts of the drivetrain, then it's useful, for example, even to relearn the values for the friction compensation, but also to check stability of the feedback loops. And okay, if there's really a very different situation to the commissioning, then okay, it makes sense to check acceleration limits too.
Nice.
But there is also a use case where it's really useful. So when you apply new controls and drives to a machine, which is called retrofit, then actually you are in a similar situation as doing the first commissioning, and here it can support you too.
Awesome. Thank you for the clarification.
All right, so as you can maybe see on that screenshot, that there's only a few parameters, and there's a reason for it. So we only want to provide the relevant parameters for the task you have to do. And so these parameters which are required here are provided. Then you can step into your tuning. And if you can't continue for a reason and or get disturbed, then you can stop it, cancel it, and then the original parameters will even be restored. Yeah, maybe you know that situation from now, that when you need to tune CNC axis, okay, you have to think about a test movement and you have to create a part program and debug it. And then when it runs, you have to think about which parameters are relevant for this task I have to do. So you have to find the parameters, you have to know the index, which is effective right now. And then after you have done the test movement, you need to record the movement. And for that, you need to know relevant signals. And finally, you need to get it on the screen to judge it. And then that might be also a feedback loop. So yeah, for that, you need to have some knowledge. And that's the part that STC will do for you in the future. So what is our basis? So we assume that, okay, the machine is mechanically finished. The drives and control, they have been set up, so axes are moving. If you like, you can do the compensations like lead screw, pitch error compensation at that moment. And then, in my understanding, the dynamic part comes last. So when we talk about these dynamic effects, then we talk about topics as stability and responsiveness of my speed loop and position loop. You want to have a quick movement, but also smooth, and you don't want to see a big overshoot when arriving in the position. And finally, okay, you want to do a contour. That means you need to sync the axis so that you actually get the wanted contour and that accuracy you require. So these are the questions for our tuning application. And finally, okay, you will check some of these requirements on your test part, and maybe you have to come back and do some fine adjustments. So if you have seen something like that, then you're exactly right here. When we talk about tuning, it's not only about making the machine more productive, but also producing good parts with the meaning of having a good surface. And seeing these surface issues is really hard to measure. It's really micrometers that cause these marks on the surface, and in some situations you even have to have the right angle of light to see them. Nevertheless, if your customer will not accept that part on the left side, you have to do a tuning job to reduce the vibration and get a shiny workpiece. So what I want to say is it's really about micrometers, and especially CNC machines and maybe especially milling machines really need high accuracy. So we are talking about some micrometers of overshoot, and it shouldn't be too slow. So that's our challenge. On the real axis, it looks like that. You can have vibration, or you can make it better. Okay, but that's about the introductions. Then let's switch to the live part. Any questions so far?
Well, on the last slide, it was kind of interesting. When you showed the response, I saw that first you had something like an underdamped response, and in both cases there was some overshoot. Once we tune the axis, what do you think is ideal? Do we go for a strategy that's overdamped, where we really have no overshoot at all, but we don't have as much responsiveness from the axis, or do we have a sweet spot like critically damped, though there is an amount of overshoot that could actually leave a mark, maybe one of those microscopic ones on the part?
Yeah, that would be probably the typical goal to have that kind of compromise which you have described. It's hard to give a clear proposal. I think that's the part where you need to decide for your access and for the requirements of your access what you can accept.
Sure.
One thing is for sure, if you decide for a really well damped arrival, then your cutting time overall will grow.
Right.
So the more movements you have, it will sum up, and then finally you will be disappointed seeing the final cutting time. And then you have to remember, okay, what we see here is kind of worst case scenario. So if you have bigger parts which have like smoother contours anyway, then you can even accept a small overshoot and you won't see it on your surface.
Sure. So there's trade-offs, is what you're saying. Is it you could trade off a longer part program time for a smoother surface by really damping the signal a lot and having no overshoot, or we could tune it more aggressively and shorten the time, but potentially have a bit of overshoot.
Right. And I think the challenge is that when starting the tuning, you will not know about the focus you need from the beginning. I think you have to start with some idea, then do the basic tuning, cut apart, and then you will get an idea whether you need more precision or more productivity.
Right.
Okay, then I will switch to STC. Can you see it?
Yep, it's coming through on my side.
Good. So I've already connected to the control. So in my case, it's a SINUMERIK 1, and I'm connected to the service part. And so, but this page, what you see now is on the one hand for your records, you can write down the order number and information which is useful later on, together with the tuning report, for example. And you can also give some basic requirements. It can mean you already know that your customer requires high surface quality, then you can use that checkbox, or you can also tell the software about some mechanical properties. But it's not mandatory. So we have defaults for everything. So if you just want to dive into tuning, that's also fine. And that you can do by having an overview. Okay, what has happened on that machine already? Then that you can see here, and you can also see direct links to each tuning step. And actually, the goal is to fill that list of axes line by line, but you can do it in an order that you like. I mean, you can do feedback loop tuning for all axes first and then do the others. But there is still the recommendation, and that's the reason why we place the topics like that. First of all, you should care about stability and responsiveness. So feedback loop tuning should be the first step. Then check acceleration, and then do jerk limitation afterwards. Because here when tuning the jerk limit, we look really precisely on the micrometers, and before that you should know about whether you have a reasonable acceleration limit. And besides from that, there are also other tuning features, more advanced features like adaptive friction compensation, and here are the measurement features like trace, and there is also a circularity test here.
That's an awesome overview. It actually seems to me like a lot of these elements that you can tune weren't there with AST, the auto servo tuning. Are some of these new?
Yep. they are so. Auto servo tuning covers the feedback loop tuning part and also the path tuning part. But also, I mean, you can find this circularity test also in SINUMERIK Operate. This one here has a new nice feature. It can do a one-axis test for you. Sounds strange to have a one-axis circle, but it's for the for the meaning of having that circle display as we are used to it. But this is really useful for checking the quadrant errors, especially for rotary axis.
Sure. Yeah, that makes sense. I know with the traditional circular test, sometimes you would still have to apply it to a rotary axis, maybe for robot tuning, and we would use virtual axes and things like that. That's really interesting that you can do that. Use
Right.
that right built into the tool.
Yeah, in the past it has been challenged to do a circle test including rotary axis. You had to have a coupling command connected to the geometry axis, and then a lot of axes were moving in the machine. You had to check for collision just for the reason of measuring a rotary axis.
Yeah. That's awesome. And what about the acceleration and jerk tunings? You said that the feedback and the path were part of the tool. I think some of us on the call are familiar with AST, but it'll be interesting. We'll probably let you get to it as you get to it, but I'm excited to learn about those two.
Yeah, we will do it for one axis at least. But the reason why we have put it in that workflow is when you configure the components and including the drives of a machine, you have to do some assumptions about the moved mass and about the friction. And friction is always a topic which is not really known exactly until you have the machine in reality. So maybe when doing the calculations for the drives, you better had some reserve, and then finally it turned out that the friction is better than expected, and then maybe you want to gain some percent and increase the acceleration, or at least you know that you're on the safe side and you know the reserve. And so that's for tuning the first machine of a series. That's a useful step. And then finally the jerk has a big influence on the productivity. So that's the main reason why we want to check it here. It should not be too low, because then the machine is overall slow when doing a lot of movements, especially for the small movements. The jerk has a lot of influence. So
interesting. So when I think between acceleration and jerk, I'm thinking of trapezoidal, I guess, velocity profile versus an S-shape velocity profile. And I wonder what your thoughts are on that. Is there still any use case for trapezoidal velocity in a machine tool, or are we primarily introducing some kind of a jerk limitation to get a smooth S shape?
Yeah, honestly, I would not recommend to what we call a brisk. So I mean, even if you need to have really quick point-to-point movements, you need to have some kind of vibration reduction in order to let the axis stop without a big overshoot. But I would always recommend to do the jerk limitation, which finally gives that S curve of the speed.
Awesome. Thank you.
Okay, but then I would say let's start doing the first step, which is the feedback loop tuning. And I will use my x-axis here. So I will start from the beginning, but as I said, if you have already tune the feedback loops using AST, you can load the results here, and that means we can read the results, and they can be reused for the calculations of the acceleration limit. So, but let's start from the beginning. So as you see, the workflow shows you from left to right that, okay, there is something to prepare. Then we go into measure and tune. Then you can check the outcome. And finally, you will see all the numbers that the software has derived. So let's start with that. You can see your tuning objective and also change it if you want. And here, for example, it also makes sure that the machine is ready to move. So if I would switch to the wrong mode, it will tell you what to do. So go back to jog. Here you will see the position range. We will automatically plot the software limits. But if you have some doubts to go the full range, that you can limit the range, and the software will make sure that your measurements stay in that range.
Wow. So when I look at that scale, I see a number on the left and a number on the far right. Where do those numbers come from?
So these are the actual software limits, which have been set up during the commissioning of the machine. But what we do here is we set up a virtual limit just for this measurement.
Okay. So I presume the machine's currently sitting at about minus 478.
Mm-hmm.
Wow. That's really nice. So you know where it's going to go. And maybe if you had something on the table because you wanted to tune it with an actual mass, you could avoid that by limiting your travel as you are there.
Mm-hmm.
Awesome.
And you will see a prediction of how far the axis will go, and that you can also see when we run it. So let's go to the next step. The user guidance here will always show you the next step here on the right side. So we will go to measure and tune, and here there's nothing to do but starting the process. Now, as you can see, the measurements will be prepared, so there is no manual work to do to set up measurement parameters. They will be derived automatically. And then, okay, the message tells you to press cycle start. And so this procedure has been started. Now, okay, you will see the overall progress, and you will see how the axis is moving. So we have to stay now for maybe 2 minutes here, as the software will make sure that all the required measurements will be done one after the other.
Sure.
So
I appreciate that progress bar. That's pretty neat. I don't recall having that in the past.
And you can, if you think that there is some trouble on the axis, or for whatever reason you need to stop, you can use that stop button, and it will stop at that task where you press the button, and then it will ask you, okay, what happened, and you can decide to select different measurement parameters. Maybe you had the impression that the axis was too fast, and you want to be more on the safe side to be able to watch it, or maybe it was too loud, so it means the noise we apply had too high of an amplitude.
It's kind of interesting to look at the overall progression of measurement as the screen's going here. I can see that we're measuring the speed plant, and then we're going to continue on to measure other things as we go. I wonder what are all those 6 phases that it's going through?
It's first of all, we need to learn about the resonances and the total inertia that the motor will see. So from speed loop point of view, tuning the single motor would be the easy part. It's like a single inertia, and it's maybe only has one resonance. But so we need to learn what is attached to that motor shaft. So
Okay.
the first two measurements are about learning the dynamical behavior of everything what is attached, and we do that in 2 steps to get the best available resolution of the frequency band. And then finally, okay, we retune the speed loop. Then we do another speed step for some estimations, and we also tune the position loop.
Interesting. So for the plant, do you need to have a secondary encoder, or is it possible to do that with just the motor encoder?
For the speed plant, motor encoder is good enough. If there is a second encoder, it's always good because then we do an additional measurement. It's called mechanical response. So then you can see the mechanical system without influence of the feedback loop. So
Awesome.
anyway, for measurements and tuning, it's always recommended to enable the second encoder if there is one attached.
Good to know. Thank you.
Okay, here you see just a quick preview of the most prominent numbers like the speed gain and integral time and position control gain, and also the total inertia which has been derived. And you can also see the body diagrams if you know them from the past, from AST, or if you know them from the books. So you can have a look more precisely about, okay, how was it tuned, whether you like it or not, speed loop and also position loop. And then if you're finished, okay, you can go back to the tuning screen. And as you can see here on the bottom, it takes you to the final step, okay, which is called finalize. And here we show all the numbers that will be touched by the tuning. These are now only the changes, but okay, if you want to see all feedback loop related numbers, you can enable that here. And you can see that there are many possible parameters that we can touch. So finally, yes, it's about confirming it, and then these numbers are enabled and active in this access and drive, and that user guidance will take you to the next feature, which is acceleration tuning. So let's step to the next one, and it automatically pre-selects a method which is called guided tuning based on calculations, because we now from the feedback loop tuning measurements, we know the total inertia, so we can do a first calculation for the maximum available acceleration. And that's actually also a new nice feature. I know from my customer visits that you like to check various situations or worst case scenarios, and to have the maximum workpiece on the table, it's always the worst case scenario. So, okay, the machine builder has defined a maximum workpiece mass, and we are talking about a moved table, then actually you would have to have that mass, and it also needs to be mounted on the table to actually test it and see how much acceleration is suitable for that. But in my experience, that always is an issue to get really that maximum piece on the table. And for that reason, we invented here a feature which estimates the friction of the actual axis and gives you a proposal for the acceleration that you can go. And if you tell the software about the maximum workpiece mass, then the calculation will also be done for that worst case scenario. So we tune with a typical part, and you just type in the number for the maximum mass, and you will also get the calculation for that. Here on this machine, I don't have a moving table, so therefore this mass is 0. But I can show you the procedure. We want to make sure here that we don't damage the mechanics right at the first movement. So I mean, what we can do naturally, we can read the limits, the electrical torque limits and power limits from the drive and the inverter, and that will give that number here. That's the minimum of all these limits we have. But we don't know anything about gearboxes or whether there is a special component, coupling, gear, whatever, that cannot have that torque. I mean, normally you should, if you have that situation, you should limit the torque in the torque limit of the drive. But if this has not happened yet, okay, you can tell us, oh no, you can't use that. You can only use 50 or whatever. So in my case, I'm safe. I can use whatever higher number to make sure that the electrical limit is our actual limitation. And then typically all people I know doing that job, they feel quite well when having some reserve in torque. So that's presetting. You can change it to whatever number you like. And now here we come to a kind of hen and egg problem. In order to derive a reasonable acceleration, you have to move the axis in a quick way. So you can't do that smooth, but we don't want to push it too hard either. So there is a presetting of the jerk limitation depending on the size of your axis. But if you have already some experience, I mean, you can change it. So, but the focus is on finding as much acceleration as it is possible for this axis. Okay, we need to have some initial numbers for the first movement. So imagine that you have no idea about how much mass will be moved, and for that the software has to find the initial settings. And so we will have two test programs. One is to do the initial measurement to judge the friction, and the second one is then to test the final result. So the first program, it tells me I should test it, so I switch to auto mode. It has been already enabled on the machine, so I will check that program, and it runs. And the important part is that finally you should feel well to keep the override on 100%. So we do the same for the second program, and here it also tells you make sure you do it slowly first, and then finally you need to keep the override on 100%. At that second move, we will use full speed, okay, which is not so fast in this axis. Okay, the program works. That means I can continue to the next step. Now that's the situation that STC will now activate new values. So up to now, all what we have seen before was preparation, just collecting numbers, but now we make it effective. And okay, now it's these two new numbers are effective in the axis settings, and I do the first measurement. For that, the first test program will be automatically activated, and now I can check what the software will find. The software recommends to have a acceleration of 3.6. So when I accept, I will take over this recommendation, and now I can go to the second step, which is just a test about how good that first estimation was. So it will enable the second program. And let's see how it worked. Great, it says goal achieved. So goal achieved means there is at least one peak of the torque is in the wanted area of 80% torque usage. So that green band is just a little bit bigger tolerance area around the 80%. So the red dotted line is the absolute torque limit, and arriving in the green area means okay, you have found a good number. So actually we have already found the best number, but okay, if you like, you could also play around with it and find out, okay, what does it mean to have a little higher acceleration, and you can do these kind of tests as often as you like. And that way you get some experience of how big you should how big the numbers are typically, and how big the change can be. So now the negative torque is over the green band, so that's why the software says the torque is too high, so we don't have the 20% reserve completely anymore. And so now we went from the lower green line above the upper green line. But anyway, I think it's still a good number, so I will accept it. And then we can continue to the next step. And so we will see this number in all dynamic groups for the acceleration. We don't use a difference in the dynamic limits here, but in the next step, in the jerk, we will see that there is a bigger scaling in these dynamic groups. So you can still edit it if you like, but if you're satisfied with that, you confirm, and then you're done with your second feature. So it also tells you the time and date, so that's important for your report later on, or when you open your tuning project offline, so then you can see when that happened. So let's continue with the jerk tuning. Here, that banner that tells you that it would be best to have a load side encoder, means a second encoder at the axis to see more precisely how much vibration you really have on the axis side. In this machine, we don't have that, so okay, I know about it, so I can delete that message. And now let's step into the jerk tuning procedure. And it's very similar to the other procedure. So there's also a preparation step. You can decide about initial settings. I want to go with a high number first, so I just use what is live on the axis now. And so axis is ready to move. Everything is fine. And now there's only one part program. So I transfer this program, and I also should test it. It moves into the middle of the range, and then it does 3 little steps. And these little steps are quite aggressive for the mechanics. So if there is a vibration, we will find it in one of these steps. When changing to the next page, we will apply the initial numbers. So now these numbers are active, and I can start the measurement. Okay. Yeah, as I'm mechatronics engineer, it's always nice to see that kind of vibration. That gives a smile in my face, but you don't want to see it on your workpiece. So you would rather reduce the jerk to move more smooth, and then we could do that next. And then you will see that, yeah, the vibration is gone. There is a small overshoot about 1.5 microns, which in my opinion is acceptable. And so that's the trade-off you have to find yourself. How low of a jerk do you really require? And for that, I think you need to get some experience about various axes, small axes and big axes, and then you will have more of a feeling of what kind of behavior is suitable for that kind of axis. So this workflow here enables you to do these experiments really quickly. You have the number to change. You will get some seconds later, you will get the trace result. So it should be a smooth workflow.
I feel like I may have just witnessed magic, but I'm not sure, because I'm looking at that curve diagram you have there, and for a moment I saw the step diagram, with I guess multiple periods in it, and that's what I always see when I'm tuning in the trace. But then all of a sudden it zoomed in right to the perfect spot. Was that something that you did, or am I?
No, it's
part of the tool?
it's done by the software. So when I do an auto scale, you will see the steps. You will see we do 3 different steps, and
Right.
if I would have to do it manually, I would have to zoom in a couple of times to see the interesting part, and then maybe do another zoom in time direction. But
Yep.
that's actually done by the software.
That's amazing. That was really neat to see that.
Okay, yeah, then you can continue here. There's not much to check here. And here you can see now the software does some very basic scaling for you. So it will stretch the numbers, because what we have seen on the last plot is really the very precise part. So we are doing kind of worst case test if the axis needs to stop in a pocket or on a surface. If, for example, the vertical axis stops on a surface, you don't want to overshoot it in position. But that only happens if you really do that step. But if you do constant movements, it will be much better. And anyway, if you do roughing, you know that more of cutting processes will follow. So you don't care about some micrometer of vibration on the surface. If they will follow anyway more programs to cut. So therefore, when the machine users switch to roughing, they expect that the machine will be faster. So now it's your job, or job of everybody who is doing the commissioning, to find appropriate numbers. What does it mean? When you do roughing, how fast can we go? How much of a jerk is good? And some compromise for semi-finishing to make sure that the vibration which is remaining can still be taken off by the last cutting part. So that's only a pre-setting. So finally, you have to find your numbers yourself by doing cutting tests. And sometimes the jerk is even too high, not because of the workpiece, but because some part on the machine doesn't feel well when shaking all the time.
Sure. So this part's actually really interesting to me because I think a lot of the attendees on the call probably know about our compressor functions, and maybe they've used cycle 832 in the past. Maybe they have advanced surface or top surface. Do these different dynamic groups, dyne norm, dyne pos, dyne rough, for example, do those tie in to cycle 832?
Exactly. When the machine user switches his programs and switches to the different mode by using cycle 832, then it means that exactly these numbers will be enabled. And,
Wow.
and that's the point, that someone has to set up these numbers. So and now here we are talking now.
This could be used as a part of the advanced surface calibration, really, is when we're trying to set this up. We don't know where to start. That this certainly gives us an idea.
Mm-hmm. Yeah, especially if you get the feedback from the customer that he feels that roughing is still too slow, then you can have a look at that jerk number here.
I really like how it ties in with those charts too, so you can see the overshoot. It's not really just guess and check.
And if there is a situation where you think that's not useful and you like to cancel, as long as you see that cancel button here, it's still possible to revert all these numbers to the original numbers, and then you can go on from the beginning. But now, okay, when I confirm it, then actually we have done the basic tuning for the x-axis. So when I go to tuning overview, now we can see, okay, the first line is done, and I've already done the feedback loop tuning for the y-axis, which is actually a gantry coupling. And so I could directly step into acceleration here or jerk and continue with my tuning steps. I think that's all what I wanted to show you for regarding the tuning. Yeah, please keep in mind that we will also provide the trace application here, and you can add all kinds of signals, PLC, servo signals, NC signals. Maybe I show you something I've already done. So here, finally, when you did the recording, you can see here also the overshoot, but I've added some more signals like the current or the power, and you can scale each one individually, and you can even define how many scales you want to see. You can say, okay, I want to see all scales, and I want to see some of the scales you want to see on the right side, maybe because it's a different unit. So you can have the power, for example, and the torque scale on the right side. So you can configure a lot of stuff on that application too.
Okay, what about importing and exporting? What if I want to share traces with someone else? Am I able to do that?
Sure. So these traces here are also saved as XML files, like you know from SINUMERIK Operate, but you can also export them into a CSV file. And when you get files from a colleague maybe and who has used SINUMERIK Operate, then they are compatible. You can load them here, so you can exchange files. It doesn't matter whether it is saved by STC or saved by SINUMERIK Operate.
Yeah, this is really interesting. It is a lot different than the trace tool that I remember in the earlier versions of Operate. It looks a little bit more aligned with the new Trace tool. You showed some of the zooming features a moment ago, but I understand that you can do things like a fast Fourier transform and FFT and even some more advanced features. Could you speak to that a little bit?
Yeah, sure. Yeah, yeah, the frequency analysis is useful. Yeah, when you have signals that don't show a clear dominant vibration. I mean, in that case, you could easily place cursors there and derive the frequency from that time. But when you have a signal that looks like noise, it could be consist of many frequencies, and for that to see what is the content of frequencies in that signal, you can use the Fourier transform. So let's see whether I have an example for that. Yeah. Yeah. Okay. Here it's also y-axis. It's not so noisy, but anyway, if you like, you can enable the Fourier transform, and then these cursors give you a time window. That means you should limit that time range to a periodical part, and then you can see how the Fourier transform is calculated live. And here you can see the frequency content, which is around 1920 Hertz. And I think I can also derive that from the from the cursors directly. Yeah, so here I can also see it, because this is the easy use case. But I'm sure you will have signals, especially from the drive or from the spindle, that look like a noisy band. And then if you see that, just remember to switch on the FFT, and then you will see exactly which frequencies are there.
That's so cool. So if you wanted to attenuate a specific frequency, given this tool, you might be able to identify it and then perhaps create a very specific band stop or notch filter, if depending on the trace you're looking at, right?
Right. Yeah. Yeah. You can do that. And there's also one, not only one. There are several use cases using the mass here. So I mean, some easy use cases are if you want to transform some units. Let's say you have only recorded the motor speed, but actually you want to know about the axis velocity. Then okay, you need to get the numbers from the gear ratio and from the lead screw pitch, and then you can transform the signal from the drive into the signal of the axis. And you can do similar stuff by, for example, you can integrate across the power, and then you get energy, or you can differentiate. If you just have a plot containing the position, from that position signal, you can do one differentiation, then you get the speed, another one for acceleration, another one for jerk. So especially if you're offline, I mean, if you're in the office or on business trip, sitting with your laptop, and you get a file from somewhere and you want to know more, then you can do some mass. I think I did that for speed. And here on the bottom you see the equations I have applied. So actually the one you see here is not smoothed yet. I did 2 times differentiation of the position, and so that gives that acceleration triangle. But I didn't like it because it looked kind of noisy, so I was applying some additional smoothing here. You can use an averaging filter, and then you get that purple curve, which looks nicer. And okay, regarding the units, okay, it shows the same numbers, and so you get an impression about which acceleration you have reached during this positioning here.
Wow, this really is a professional tool. It has lots of awesome features that go beyond what I'm used to seeing in the older trace tool. I have just two more questions before we probably might want to proceed to the official question and answer period. The first is the way we're looking at the tool now primarily presents itself like an offline tool where we can analyze traces that maybe come from other spots. They could come from the control itself, the operate trace tool inside it, or maybe from our colleagues. Does this tool also have an online mode where we could connect our PC and use it in that way? And then the second question relates to licensing. We saw two different products, I think, today, or at least two different parts of this package. Are they the same or are they different as far as licensing goes?
Yeah, maybe let's go to the first part. I think you were asking about whether trace can go online, right?
Yep.
Yes, sure. So yeah, actually, when STC is online, that trace application is also online, and so we can do that recording again. Actually, so it was about y-axis. So, and did I have a trigger? Yes, I had. But let's just do a new recording, and I will show you. So we are online. We can take position and maybe torque, producing current, and select the axis. And the most simple way, I could just start the trace and move the axis, and then you will see how the trace signals will arrive on the plot. And yeah, so it's mainly made for recording and visualization, but yeah, it also has some offline analysis features. Okay, and then let's come to the second question about the license. So the good news is when you download STC, you can start right away, and there are two licenses. One is for the basic tuning, and the other one is about expert trace. But don't be afraid about trace. So the typical tracing, recording, zooming is possible without any license. You can do that after you got STC. You can do traces and save it and give it to colleagues and so on. That's not an issue. Expert trace is required for Fourier analysis and for the mass operations, for the CSV export, and also to get more variety of cursors. So expert licenses, expert trace is really optional. But for tuning, you definitely need the basic tuning license. And here you can, in STC, you can start the trial license, which is 30 days for your tuning. Then you will have ALM licenses. So when you order it, you can order it by using these MLFBs, and then you will get an ALM license, which you see in Automation License Manager, and then you're set up.
All right. Well, that is a very descriptive and great presentation, guys. Shall we progress to the Q&A section? We did have quite a few questions come in from the audience. Sound good? You guys ready for it?
Sounds good to me.
All right,
Yep.
perfect. So let's get in it here. Starting with the oldest, can this tool fix chatter issues? So I guess chatter issues that are being experienced during cutting.
Yeah, generally spoken, it's you can vary the feedback loop aggressiveness, but there's not a specific method for reducing chattering.
Perfect. I guess in some respects, though, we can use certainly the tools built into it, allow the trace functionality to at least be able to visualize the chatter during a cut condition, right?
Yes.
but
I mean, there are features that will modify the feed rate, for example, to prevent chattering. So that would be the solution. But in the tuning, you can only try to get maybe more damping in a specific axis. For that, you have to find out, okay, which axis is involved, and then select a tuning objective with more damping.
Perfect.
Mhm.
Daniel had asked how to know if STC, SINUMERIK Tuning Center, is needed versus the tuning tools in Operate. So I guess when would you make the choice from moving from one to another?
If you're already familiar using the tuning tools in Operate, I mean, they provide a lot of parameters, and you can, if you are able to play on that keyboard, then you're fine. The question is if you're more like a starter in SINUMERIK, and you don't want to learn about all the measurement settings, then you should rather start with SINUMERIK Tuning Center.
Are there other use cases for maybe advanced users where the tuning center would make sense over still doing everything with AST?
Yeah, mainly for the reporting. So
Mhm.
Tuning Center will provide you a report including acceleration and jerk, and also adaptive friction values. So that will give you more information. So you can even tune the machine manually, and you can go online with STC and just take a snapshot of all the numbers which are live, just for your document.
Perfect. We have another question here. For example, after AST, we have standstill humming noise. Does this new software tool fix that issue?
We are working on it. There are various reasons why you can have that noise. But one thing which is new in STC is we have a new tuning algorithm that gives a better compromise of gain and stiffness of the loop. So my assumption is that when you use that new algorithm for the higher stiffness, then you will end up having a more moderate gain, and that has more reserve with respect to stability. So if your noise was because of too much gain in the speed control loop, then that should be gone after tuning with STC.
Perfect. Does this new software tool figure out whether machine mechanics are good for moderate or aggressive tuning?
There are some basic rules based on the machine size. So actually, the software does not know a lot about the mechanics. So we will learn that during the measurements. But there are some presettings. So, and that's coming back to this machine description page. So in the machine description page here, you can tell some specifics about your mechanics. And for example, if you know already that your axis has high friction, then, and you also know that besides from that you need high surface quality, that will give you a presetting of aggressive tuning.
That's cool. Okay, it's probably a better question for Brian. So they're asking, where can I learn more about Siemens and drive systems? So where would you point somebody to learn more about us? Especially, it sounds like more from the commissioning and integration side, I would guess.
Sure. So generally, a great spot to learn more about anything Siemens would be cPortal. So we go to cPortal.
You're not sharing anything, Brian, by the way.
Oh, right. Let me fix that real quick here. I'm going to share my screen, put up the entire screen, and here we go. So this is a wonderful spot to learn more about any and all things to do with Siemens. To get into it, the first thing you're going to want to do is log in. And if you don't have a registration already with us, you can create an account. A lot of the information is available without having an account, but to save favorites, request real support from a live representative and do things like that, it's real nice to have. But here we could look at SINUMERIK drive tuning, for example, and be sure to look at the knowledge base. And we're going to come up with some hits here, I'm quite sure, between the commissioning manual and even the manual you see here on how to use the SINUMERIK Tuning Center, which we just talked about. I would also say that there are so many resources available through the team that Chris leads, that I'm on and happy to be on. We have some documents called Train the Trainers. They go over different workflows for different CNCs, all to do with the mechatronics optimization. So there are some documents available, and hopefully those are helpful to you.
Yeah, no, that's perfect. And I think this leads into his next question. He was also asking, where can you find these PDFs? So obviously cPortal is hosting all kinds of white papers and knowledge content, as well as all of our core manuals and PDFs. So certainly if you're not familiar with it, you want to go over to cPortal and explore that. Okay, back to question on the software at hand. Can we manually adjust and correct feedback loop parameters through the software, similar to what we can do using AST?
No.
Well, there's an answer.
Yeah, it's that's actually a challenge for us. On the one hand, we had a focus on making it as easy as possible. On the other hand, we know that in some situations you need to do some adjustments, and the key question is how many of the parameters, and you have seen that there are many feedback loop parameters, how many of them should we offer? All of them? Or and for that, if you're on that kind of level, I think you should use AST, and you can do whatever you like. Yeah.
Got it. Nope, perfect. Hey, it's not everything for everyone. You got to know when to leverage the right tools and when to use the other tools we have. Hence why we didn't get rid of AST, right? All right, so let me just say, so this one, is there an easy application example of when I would choose to use a workflow like STC over CC Roku? It appears that the visualization tool inside of STC are pretty impressive, comparatively speaking. It looks like some of the things Roku solves, this could be also fixed. Very cool demo so far. Any thoughts on that one?
Nice to hear that feedback. Yeah, I think when is Roku do we talk about robot control?
That's what I think of when I think of Roku.
Yeah, yeah. So I think for controlling robots, you need some special software, and actually the specifics of the robots are that the inertia which is seen by each motor depends a lot on the position of the arm, and that requires like a live adaptation of the feedback loop parameters. So that's really next level.
So we would probably then say, from a robot optimization or tuning perspective, we would not be using STC for that application. More traditional machine tools, at least to date, right?
Yes.
Mills,
Yes.
lathes, grinders, that kind of stuff.
Yes.
Good. There was a question on where can we download this software. Can it come from cPortal to get the trial version and all that?
Yes.
Okay, perfect. So I guess if we do a search on cPortal for the Siemens Tuning Center, it should pop right up.
I hope so. Yes.
Looks like Brian's pulling it up here.
Yep, I'm on top of that. We have the first hit when we search SINUMERIK Tuning Center is the delivery release note. And when we scroll down here, the download you'll find right at the top. Yep.
Yep. And
So
you guys said we got a
easy.
temp license initially when we bring it down. How long is the temp license good for again?
30 days.
30 days. So we can do everything for 30 days. And by that point, we should know if we want to buy it, I would think. Perfect.
Yep.
I think I got through all the questions. There were a ton. We certainly appreciate it. Oh, no, maybe another one popped up. What is the cost of the basic tuning license? So I guess the first license option. Any idea from a market side? I mean, this could change region to region, but do we have a ballpark?
I can only say don't be afraid of the cost. I mean, it's really moderate price.
Okay. So certainly I would suggest then talking to your local Siemens organization. Again, we have people on these these webinars from all over the world. So get a hold of somebody from your local area, and we'd be happy to quote it for you. But to Alex's point, it's not going to break the bank, is what I'm hearing, which sounds great. Okay, I think I got everything. For sure, if I missed it, I would say just reach out to us. We'd be happy to talk to you guys further about any and all of these products. I want to just thank Brian and Alex for an awesome demonstration. I love the dialogue between you guys. Everything really went well. I think our audience learned quite a bit here today. And with that, I'd like to thank everybody for joining us, and we look forward to seeing everybody real soon. Have a great weekend. Take it easy, everybody. Bye-bye.